Hey everybody, this is day 9 of the astronomy unit. I'm Andy Pilc, and in today's video I'm going to be going over a couple of the concepts that were covered in this lesson on orbits. In order to do so, I'm going to get some help using this PhET simulator called Gravity in Orbits to just cover a couple of the key understandings when it comes to orbits and gravitational attraction. So in order for a planet or any celestial object to orbit around another celestial object, we're going to need two things. The first is going to be the force of gravity, and the second is going to be velocity, which is speed, and that velocity is going to be at a right angle, or it's going to be perpendicular to the force of gravity. So there's a lot to kind of cover here. We will kind of start right from the beginning. So let's turn the grid on and the path on. Now, first off, when looking at the force of gravity, one thing to remember is Newton's law of equal and opposite forces. So a lot of times we say that the sun has a gravitational pull and it pulls on the planets and keeps them in orbit. In reality, both of these objects are pulling on each other with an equal amount of force. The only difference is that when you look in the ESRT, the sun is so much more massive than the Earth that the gravitational pull is actually going to affect Earth way more than it affects the sun. But we will see some little differences if we were to compare the orbit or the gravitational attraction between like the moon and the Earth. We'll take a look at that in a little bit. But a couple of things that will affect the amount of gravity is one, the mass. So if I increase the mass of either one of these celestial objects, if I make the sun more massive, you're going to notice that the force of gravity is increasing, and it's increasing in both directions. So when the sun is pulling on the Earth with a greater force, when I increase the mass, the Earth is technically also pulling on the sun with an equal force, an equally increasing force. And the same would apply if I were to make the planet more massive. So it doesn't matter which one is gaining or losing mass. The more massive the celestial objects are that are involved, the greater the force of gravity is going to be. The second thing that's going to affect the amount of gravity or the amount of gravitational attraction is going to be the distance between the two celestial objects. So if I move the Earth closer to the sun, you're going to see those blue arrows showing force are going to get longer. So those are vectors, meaning the longer the arrow is, the greater the attraction. So even though it's going through the sun, that long arrow between the Earth and the sun here, that's just showing me this increased amount of gravitational force. So, and if we didn't have that gravitational force and we just had the velocity, then Newton's law of inertia tells us that that planet is going to continue on that path unless there's a force that changes its direction. And luckily for us, that force is going to be gravity. So we can use this model to take a look at orbits. And another thing that you're going to, actually before I continue, let's just talk about that one little difference between the Earth and the sun, and let's change it to the Earth and the moon. So when we're looking here, still the same concept applies, that the more massive either one of these things are, the more gravitational attraction there's going to be. The closer they get, the more attraction there's going to be. So another thing that we can see in the simulation is that the path that the Earth is taking around the sun, the orbit, the orbital path, is not a perfect circle. And I can tell using this grid because the distance between the center of the sun here and where the Earth is in its orbit here is 2 boxes. And over here in this part of the orbit, it's just over 2 boxes. And we actually see that in all of the orbits of the celestial objects in the solar system. They're not perfect circles. They're just a little bit off. We call them ellipses. And in order to talk about the differences at the different points in an orbit, I'm going to exaggerate this elliptical orbit just a little bit more to take a look at how that's going to affect the gravity and then the velocity. So in this situation here, we see that there is a pretty big distance between the Earth and the Sun. So it's almost 3 boxes here. And if you notice too, the blue arrow showing us the amount of force between the Earth and the Sun, it's relatively short. And as the Earth comes into this part of the orbit, we're going to see this blue arrow getting bigger, showing us something that we already know. When it's closer to the Sun, the gravitational attraction is going to be more. And another difference that we can see here, maybe we'll exaggerate a little bit more, is that it's going to be moving faster as it's closer to the Sun. So we can see at this part of the orbit, right up on the top, looks like it's where it's the closest to the Sun. And if we check out the length of this vector, this velocity vector, it's 1, 2, 3, almost 4 boxes long, showing us a pretty high velocity at this point in its orbit. And then if we continue, we're going to see those blue arrows grow shorter over here, showing us the lowest amount of gravitational attraction. And with that is also a lower orbital velocity. So when it was closest, it was about 4 boxes long. Over here, when it's in this orbit, the slowest point in the orbit and the furthest from the Sun, we're going to see the slowest vector here. We're going to switch over to the 2-scale part of the simulator for this next part, just to kind of look at one more difference between the orbit of the Moon around the Earth and the orbit of the Earth around the Sun. So if we were to look at the Earth around the Sun, again, it does look like a similar shape to the one that we saw in the model. But something I do want to point out is that even though the orbit is causing the Sun to have a bigger effect on the motion of the planet, you'll notice that there is a really tiny v velocity vector for the star as well. So that's because that even though the tug of the Sun on the planet is more significant than the planet on the Sun, there is a tiny, tiny effect. And we can see that a little bit more in the Moon simulator here. So if I were to pause this and just move the Moon a little bit closer and increase the amount of gravitational attraction, I can increase the speed here too. Oops, I just lost my Moon. Let's see if it stays in place here. So you're going to see a little bit of an effect on the velocity of the planet, and it even traces the path too. So even though this larger planet, since it's the mass of the Earth, we can call it Earth, even though the planet is having a bigger noticeable effect on the orbit of the Moon, since the Earth is so much more massive than the Moon, the Earth is 100 times more massive than the Moon, it's going to have a bigger effect than the Moon will have on the motion of the Earth. Just like even though the Earth has an effect on the motion of the Sun's effect on the Earth is going to be so much more greater because the Sun is 333,000 times more massive than the Sun. And if you continue to zoom out, everything in space is kind of orbiting around something else. So even though we kind of call our Sun the center of our solar system, that star is still orbiting the center of the Milky Way galaxy if you were to zoom out a little bit more and track the motion of the Sun in space. And if you were to zoom out even more, you can even see how the Milky Way galaxy orbits other objects even bigger throughout the universe too. So we'll take a look at orbits a little bit more in the next coming lessons, but in this video we just wanted to cover the basics and talk about how Newton's laws come into play when we're discussing orbits and velocities. Hope you found this helpful, and I'll see you next time.